Operation Oracle consists of two connected systems. Let's meet the first device of Operation Oracle. NOMA AI is a portable device that analyzes skin lesion using explainable AI longitudinal tracking and adaptive skin tone calibration. It runs on a Raspberry Pi and uses a MobileNet v3 neural network trained across 24 dermatological conditions. To reduce algorithmic bias, I incorporated diverse skin tone datasets and validated performance across Fitzpatrick categories, reducing the accuracy disparity between dark and light skin to just 2% in the test sets compared to over 34% reported in some commercial systems. But here's what makes NOMA AI different. It has 5 explainability features. First, the ABCDE wizard. The system walks users through asymmetry, border, color, diameter, and evolution, then generates plain language clinical rationale explaining why a risk level was assigned. Second, ITA-based transparency. Before classification, the system secretly calculates skin tone using individual typology angle, a continuous physics-based metric. Users see a bias risk level indicator and know if adaptive contrast enhancement was applied when the results are shown. Third, true Grad-CAM heat maps. The red regions show exactly what influenced the prediction, not edge detection proxies but actual gradient-based attention maps. Fourth, ORB feature matching visibility. When tracking lesions over time, the system shows how many features match between scans, such as 194 out of 500, so users understand why the system thinks it's the same lesion. Fifth, a complete health passport. Every scan is saved with timestamp, prediction, confidence, and skin tone. Users can review their complete history. Most commercial dermatology AI systems have 0 explainability features. NOMA AI has 5. That's a fundamental different design philosophy. Now let's talk about THORACIS AI, the Pulmonary counterpart. It combines acoustic respiratory analysis with microwave imaging through feature-level multimodal fusion. The microwave subsystem uses a time-multiplex antenna array and nano-VNA to measure how electromagnetic waves propagate through tissue. It is time-multiplex because I use single-pole double-throw switches to determine which antennas are the receivers and transmitters, creating 4 unique paths. Because tumors contain higher water content, they exhibit different dielectric properties than healthy tissue. Initial tumor signals were masked by antenna coupling noise, signals going around the tissue instead of through it, so I implemented adaptive background subtraction to recover the tumor response. The acoustic subsystem analyzes COPD, pneumonia, asthma, and bronchitis, conditions that share airway obstruction patterns with lung cancer. It uses 2 Boya BYMS Lavier microphones embedded within primary care adult stethoscope heads. Tumors narrow airways, producing wheezing indistinguishable from COPD, and COPD itself is a 6-fold lung cancer risk factor, so the model learns obstruction features relevant to malignancy even without explicit cancer labels. I validated the microwave subsystem using 12 dynamic agar breathing phantoms and 4 ex vivo tissue models. The results? 19.4 decibel tumor contrast, nearly 4 times the clinical detection threshold, and localization accuracy of plus or minus 1.5 centimeters. I validated the acoustic subsystem with 1,211 samples from public datasets of the lung conditions previously mentioned with the model YAMNet, a pre-trained audio classifier. Finally, I fused the microwave and acoustic features using XGBoost. The results showcase that multimodal fusion achieved 97.8% accuracy. That confirms my central hypothesis that structural and functional signals are genuinely complementary. The entire system of both THORACIS and NOMA AI costs under $800 Canadian, 60 times less than a CT scanner and 12 times less than lab-grade microwave equipment. Currently, Operation Oracle is used in STEM workshops hosted by my nonprofit DetectEd, where students assemble hardware and learn about AI and bias mitigation. I've also showcased the prototype at the Calgary Youth Science Fair and Canada-wide Science Fair, winning gold and silver respectively. Future pathways include clinical validation with the University of Calgary, rural health pilots with Alberta Health Services, and Indigenous community partnerships. As a person of color, I know that many existing AI systems weren't designed with people who look like me in mind. That's why transparency, accessibility, and fairness became foundational design requirements, not afterthoughts. Operation Oracle aims to show that advanced healthcare technology can be transparent, community-oriented, and globally accessible. Thank you for watching.